We learned yesterday about the third of Newton's three laws, aptly named Newton's third law. It says if object A applies a force on object B, then object B will always apply an equal and opposite force on object A. And it is always. It is truly always. We gave some scenarios yesterday where it might not seem like it's always equal and opposite, but yet it is. You're walking across the floor, you kick the end of the bed or the bedpost. Your toe hurts. Why does your toe hurt? Well, because you kicked the bed with a certain force, and the bed kicked you back with the same force. You punch something or someone. You apply a certain force on that thing. That thing applies an equal and opposite force on you. You throw a rock at the window, and this is the one that we spent some time on yesterday. The rock breaks the window. The rock breaks the window. It doesn't mean that there was no equal and opposite force applied backwards. It just means that the force that the window applied back on the rock, although it was as strong as the force that the rock applied on the window, it just means that it wasn't strong enough to stop the rock or break the rock. A bug hits the windshield of your car. The bug squishes. Your windshield doesn't break. It's the same force. The bug applied a force on the windshield. The windshield applied an equal and opposite force on the bug. That force wasn't strong enough to break your windshield. That force was strong enough to break the bug. Make sense? We just showed you a video of a guy shooting a shotgun. When he shoots the shotgun, the gun comes back, it recoils back and hits him in the face. And we kind of laugh at it. It's maybe not really funny, but he's okay, but it hurts. Okay, why does it hurt? Well, the gun's moving pretty fast, but the gun's not moving as fast as the bullet, right? Or the shot from the shotgun, right? Why does it go backwards in the first place? If the shot goes forward, why does the gun go backward? There's always a recoil. Okay, so the shell applies a force on the gun, or well, the gun applies a force on the shell, right? And that's the action force. And then the reaction force would be the shell applies an equal and opposite force back on the gun. Well, why is it that the shot goes forward with a really, really high speed, fast enough to maybe even kill you, but yet the gun goes back with a pretty high speed, hits a guy in the face, clearly not enough to kill somebody unless it hits you in the wrong part, right? Temple or something like that. Okay, but normally not enough to kill you. Why is it that the shot goes forward faster than the gun does? Then the gun goes backwards, Jonathan? Yeah, gun's heavier. It's the same force, but heavier things accelerate at a smaller rate. The gun goes backwards, but it's not going to go back as quickly. My son and I have airsoft guns. We fire them in the basement at a target in the basement. And he expects, his is a spring-powered airsoft gun. It's still pretty good. It fires it at, I think it's 341 feet per second, which is still pretty good, right? For a spring-powered toy gun, not a toy gun, but a spring-powered gun, to fire off these little plastic pellets at 341 feet per second. That's the length of a football field. Okay, the length of that football field up there in 1 second. That's how fast those little pellets go in the basement. That's pretty good. Okay, mine's CO2 powered. Mine goes at 410 or something like that feet per second. So not that much faster, but it's CO2 powered. Okay, it's a little bit easier because you don't have to crank it by hand, right? When I got mine, my son said, oh, he was all excited about firing this because he thought, my son's 12, my son thought this was going to provide a lot more recoil, like a lot more kick, right? He plays Call of Duty or whatever and sees the recoil on these guns, and he thinks this one, because it's more realistic, because it's CO2 powered, you don't have to do it by hand, it's going to provide more kickback. Does it? A tiny bit, but it doesn't have anything to do with the CO2 power, right? Why does it provide a little bit more recoil? Well, because the little pellet's going at 410 feet per second instead of 340 feet per second, right? That means it's got to apply more force on the bullet or on the little pellet to make it go faster. Well, therefore, the pellet applies more force back on the gun. But since the pellet is so light, it's just this tiny little plastic pellet, it doesn't provide very much force backwards on the gun at all. Anybody ever shot an airsoft gun? Do you feel a recoil? No. Even though you're applying quite a force, you're applying enough force to accelerate the little pellet to a really, really high speed, it just doesn't require that much force to do that. You apply that same force back on the gun, it doesn't do anything because the gun is so much heavier than the pellet is. In the case of the video that we just saw, look, the gun is heavier than the shot, but not as much heavier as it is in the case of the airsoft, right? Because in the video that we just saw, it's a real gun, right? So the shot that's being fired isn't made out of this tiny little piece of plastic, right? Object A applies a force on object B. Object B will apply an equal and opposite force on object A, always. Doesn't mean they're going to accelerate at the same rate. Doesn't mean they're going to move at the same rate, object A and object B. It just means that the force on object A is the same as the force on object B. I want to do a little example of a question here that is kind of a mathematical problem that we can use this qualitative law to use, to solve. Now, this is a problem that some of you probably could have solved 3 or 4 days ago. 3 or 4 days ago, you knew pretty much everything you needed to solve this problem. There was one thing that you were missing, and that was Newton's third law. Everything else, the mathematics of it, we had 3 or 4 days ago. We had it last week, the mathematics of it. This question says, Mr. Dickie's mass is 70 kilograms. Let's pick one of you. Let's pick one of you. Who are we going to pick on here? Dom, what's your mass? 60? Okay, let's say 60 kilograms. Okay, Dom's mass is 60 kilograms. Dom pushes Mr. Dickie. I don't know why he'd want to do that, but let's say that he does. He pushes me, causing me to accelerate at 2.5 meters per second squared. What's Dom's acceleration? What's his acceleration? Hey, let's make a prediction before we actually solve this. Do you think Dom's acceleration is going to be more than mine or less than mine? Higher or smaller value? Why do you think it's going to be more? Ben? Good, good. We can look at that on 2 levels, okay? In the end, A is equal to F over M. The force is the same. If the mass goes down, and Dom's mass is less than mine, if the mass goes down, then the acceleration must go up. You can look at it on another level, inertia. Inertia is the tendency of an object to keep doing what it's doing, a tendency to resist a change in motion. Who has more tendency to resist a change in motion? Me or Dom? Who has more tendency to resist motion? Me. Why? Because I have more mass. Inertia is related to mass. The heavier something is, the more inertia it has, the more it wants to resist a change in motion. So forget about the equation for a second. Who resists a change in motion more? Me. That means I'm going to accelerate at a lower rate than Dom. So notice what we've just done. We've just done Newton's third law. Object A applies a force on B, object B applies an equal and opposite force on object A. But in determining who's going to have a bigger acceleration, object A or object B, we related that back to Newton's second law, A is equal to F over M. We also related it back to Newton's first law, which is that law of inertia. So these 3 laws, although they seem like 3 separate laws, and they are 3 separate laws, they are very intricately related to each other. One affects the other. They're different laws, but they're not completely independent of one another. The third law is dependent on the first law and the second law. All right, let's solve this problem. What do you want to do? What do you want to do first? Listen, a week ago, you could have done something for this problem. You might not have been able to solve it. Maybe you could have. But a week ago, you could have done something. What's that something that you could have done a week ago? Hugh? Find the force that I get pushed with? Okay, so let's do that. So let's say the mass of me is 70 kilograms. My acceleration is 2.5 meters per second squared. Let's find my force. And that's pretty straightforward, right? Say F is equal to M times A. So we're going to say 70 kilograms times 2.5. That gives me a force that's applied on me of, what's 75? Well, how is that helpful? That's not what we were looking for. We wanted Dom's acceleration, not my force. But you know what, Hugh? Even though that's not what we're looking for, I've always said, and I always will say, hey, if you can find something, that's better than nothing. So get it. We got my force, good. Maybe that's going to be helpful, maybe it's not. Worst case scenario is I just solved for something I didn't need. But now, this next step is the step that you might not have known a week ago. Yep. Michael? Why do you want to divide by Dom's mass? Good, the same force, right? Dom's mass is 60 kilograms. The force acting on Dom, we now know is 175. Or is it? Is it 175? Oh, it's not. Oh, but it's close. Yes, because it's equal and opposite. So Dom's force is negative 175. We're trying to find Dom's acceleration. We're going to say A is equal to F over M. The force on Dom is negative 175 newtons, and the mass of Dom is 60 kilograms. We divide those two numbers. Negative 2.91 meters per second squared, which we should actually round to 2 digits here, right? Negative 2.9 meters per second squared. We predicted that Dom's acceleration would be higher because his mass is lower. Is it? Yes, exactly as we predicted. Make sense? I want to leave you with one more question. Okay, this question is almost the same as what you've just seen up here, but there's a tiny bit more to it. But the good news is, the little bit extra that you have to do in this next question isn't really, it isn't really stuff that we've done recently. It's stuff that we did early on in the year. In other words, it's the easy stuff. It's the old kinematic stuff. Here's the next question. A 15 kilogram toddler gets in an argument with a 20 kilogram toddler and pushes him. The 20 kilogram toddler accelerates at 1.5. If the 15 kilogram toddler pushes for 0.55, hey, by the way, if the 15 kilogram toddler pushes for 0.55, how long does the 20 kilogram toddler push for? 0.55, right? They both push for the same time with the same force, opposite direction. What's the final speed of the 15 kilogram toddler? You're going to do for this question pretty much what you did for the last question. You're going to end up getting the acceleration of the 15 kilogram toddler. And then from that acceleration, you're going to find the final speed of the 15 kilogram toddler, which you can get using those old group B equations that we learned maybe a week or so into school. Okay, I'm going to leave you with that today. Anytime we have left here, you can work on this. If you don't finish it in class here today, then let's finish it up for Monday, okay? And then we'll take a look at it then. Good?